Okay. Hi, everyone. First of all, I'd love to thank you all for being here today. Today, I'm going to present my work that has been accepted in the ZIP conference entitled Multiple Transform Selection Concept Modeling and Implementation Using Interface-Based SDF Graph. Through this presentation, we are going to start with an introduction. Then we will focus on the multiple transform selection concept, the definition and feature. After that, we will talk about the proposed model, shows its experimental result, and finally, of course, some conclusion and perspective. Video are taken all over the world. It's projected to account 82% of internet traffic by 2022. Actually, we can all notice the huge use of video websites such as YouTube, Netflix, the huge use of gaming platform. Especially in this year, I think this percentage obviously is going to increase due to COVID-19, which forced us to stay at home and unfortunately remote working. Also, through years, many video format has appeared. Thus, the appearance of different video coding standards, such as EVC that targets HD resolution, HEVC that targets 4K and Ultra HD resolution, and finally, versatile video coding that has just been released. Compared to the previous standard HEVC, VVC enabled 40% of coding gain for the same visual quality. And it is the standard that we are going to work with. Video coding process is a difficult one. It contains different level or different steps. But in this work, we are going to focus on the transform unit, more specifically on the multiple transform selection concept. What is it? Well, multiple transform selection concept, it has been introduced in DVC. It enabled encoder the best the transformation that minimize the rate distortion among a predefined topologic transformation, including the well-known discrete Ko-Smith transform type 8 and type 2, DCT8 and DCT2. And also the discrete size transform type 7, DST7. As you can see here in this figure, if DST7 has chosen for the first direction, DVC enables the use of DST7 or DCT8 for the second one. The same for DCT8, unlike DCT2, which is applied for both directions once it is selected. MTS has three main features, which are butterfly decomposition of for DCT2. If you focus on those equations, you will realize that the one of DCT2 is different because the transform size n is linear in this equation, which enables the recursive detection of larger block size from smaller one, thus the butterfly decomposition. The second feature is that DCT8 can be deduced from DST7 and vice versa based on this equation. Finally, zeroing out. In fact, in order to reduce the complexity of the transform unit, high-frequency coefficients are zeroed out for larger block size. By larger block size, we mean blocks of order 64 for DCT2 and order 32 for DCT8 and DST7. Okay, now let's move on to the MTS data flow model. But before getting into the detail, let's discover what stands behind this idea. In fact, to reduce the complexity of the transform unit, many optimization has been proposed. Some of them by referring one transform type from another, other by reducing the number of required operation, means addition and multiplication. However, in this work, we are going to propose a new software optimization based on data flow modeling. What is data flow modeling? Well, it is a network of computing units called actors exchanging tokens through indirectional buffered links, FIFOs. Now, if you ask me why data flow, I will tell you because data flow has proven to be useful for capturing important data dependency, exploring parallelism between system cores, and the most important thing that with the same data flow model, we could target different architecture, such as FPGA, x86 architecture, and Carlay. Now, let's, in order to, the tool that has been used to create the model is called Prism. which is an open source rapid prototyping tool that generates multi-core algorithm for embedded system. To realize our model, there are several tasks to realize first, which are the algorithmic graph, the architecture graph, the scenario, and the workflow. Let's discover them one by one. Algorithmic graph. The kind of algorithmic graph used is a static specialization of EBSDF called Interface-Based Synchronous Data Flow, EBSDF. It aims at describing the whole process by using actors and FIFOs. We managed to realize two EBSDF graphs, as you can see here, that we are going to detail in the next slides. The architecture graph. The kind of architecture graph used is called System Level Architecture Model, SLAM. It is a set of cores related to a shared memory in order to communicate. Those are some examples. Here an example with the use of only one core, two core, three, and you could use as many as you need. Now let's move on to the scenario, which is a very, very important item as it contains all the parameters that control the application performance. It contains the EBSDF graph to be used, the SLAM to be used, and the execution time of each actor. Actually, which is a very important thing as it has a great impact on the application, the performance of our proposed model. Actually, by default, the scheduling algorithm considers that all actor execution time, all actor has the same execution time equal to 100 time unit. This inaccurate knowledge of actor execution time could yield in a bad decision by the scheduler, thus a bad impact on our application performance. Okay. Now, Prism contains also many tasks in order to generate code, to display the Gantt chart, which is, as you can see, is a graph that describes the partitioning of tasks according to the number of used cores. Also, it contains some optimization tasks like software pipelining and memory optimization. Both of those tasks serve at reducing the execution time, which is our goal. So now, after doing all of that, let's move on to the result and interpretation. The first implementation was based on this EBSDF graph. If you focus on it, you will realize that the transform actor is different. Well, this is because it is an hierarchical actor. If we get inside it, we will realize that there are several actors in the inside. This fact reduces the execution time of each actor, thus a fine-grained granularity model. This fine granularity model has resulted in an execution time on one core too short compared to the execution time on 2, 3, and 4 cores, as the curve on blue shows. Shocking, right? The exploring parallelism is supposed to reduce the execution time while increasing the number of core used, like the curve on red shows, and our result shows just the opposite. Well, this could be explained by different things. Actually, in a fine-grained granularity makes every process, even though it's characterized by a short time with a great importance and great negative impact on our application performance. Actually, on this kind of graph, all the process that the operating system performs, such as allowing the application to create threads, even communicate, synchronize tasks, provide time, memory, and peripheral management tool, are considered. Synchronization in this kind of model turns to be very costly. In fact, in a nutshell, to achieve efficient performance, task management and data transfer time should not be too long with respect to the computing time. However, this EBSDF graph could yield in a good result if we send several blocks to be transformed at the same time. If you, as you can see here in this figure, as we increase the number of blocks to be transformed, we are getting closer and closer to the theoretical result, the curve on green. Now let's move on to the second implementation, which is based on a simpler EBSDF graph. It is composed of two low-level actors, means no hierarchical one. The basic idea behind this implementation is exploration of the independency between the blocks to be transformed. The result of this EBSDF model has shown an execution time on two core lower than on one core, which is our goal. We saw that we realized a speed up equal to 1.872, as you could see in this first table. Thus, the efficient, which is close to the optimal case on when using, which is two while using two core. The second table also another result that proves the efficiency of the coarse grain data flow model. Okay, those are other results for the coarse grain model. As you could notice here in this graph, the blue curve for both figures, the blue curve is presenting the theoretical result, while the red one presents the experimental result. The first figure illustrates the speed up of the application while increasing the number of used core on a 4-core machine, while the second one, the result of the speed up while increasing the number of used core while using a 24-core machine. For both figures, the experimental result was too close to the theoretical result, which proves also the efficiency of our model. To summarize, to create an efficient solution for x86 architecture, each actor must perform a significant number of calculations, means high or medium granularity. It is important to choose the level of granularity to be used according to the target architecture before modeling an application. And as a future work, we aim at using Prism to implement other units of video coding and study the fine-grained granularity effect on card array, multi-DSP, and FPGA architecture. So this was my presentation. Thank you for your attention.
Thank you very much. So now is the time for questions.
I have two questions.
Yes.
I can start. I've seen that you have the Leti logo on your first slide. Are you working with Leti?
Yes. Yes.
But not the one from the CEA.
Sorry?
Yes.
Leti, it's not the one from the CEA. Okay, okay. It's the name of the lab from
from SPAX. Yes.
Okay. Thank you. Okay. And my second question, so I'm not familiar with these topics, but usually what is the expected benefit of fine-grain granularity?
In fact, we realized two models, one with thin-grain granularity and other with a coarse-grain granularity. At first, when using a thin-grain granularity, we discovered that the result wasn't good because we aim at reducing the execution time of the application. And when we used the fine-grain granularity model, here are the results. Okay. Okay, when we use the fine-grained granularity model, as you can see here in the experimental result, the curve on blue, the execution time has increased.
So,
and this is not our goal. Our goal,
yes, of course.
Our goal is to reduce, as the theoretical result shows, to reduce the execution time, so that we have moved on to a coarse-grain model in order to have the result that we want.
And do you expect that on other architecture you will have the same result? Do you expect to have same result on other architectures?
No, we think that fine-grained granularity would be beneficial on other architecture like FPGA, but we didn't.
You have to prove it.
Yes, we didn't deal with it yet because Prism doesn't contain the FPGA. Doesn't give you the opportunity to use FPGA yet. But we are aiming at doing that.
Okay, thank you.
Okay.
I have a question on the effort that you needed to spend on migrating to your code to Prism. So what was the most difficult for you, and how much effort did you need to migrate your code?
Okay. Well, for the transform unit is for the MTS concept especially is not so difficult because that part you could easily extract from the original VVC algorithm.
Mm-hmm.
You just need to know what are the inputs and what are the outputs.
Okay,
and,
so this was
and
pretty
how,
easy to migrate. So this was pretty easy to migrate this switch between different excluding tasks or something like that.
Yes, the only thing that I extracted the code of the MTS from the VVC, and then you have to study what are the things that could be used in parallel.
Okay.
So that, for example, if you see here, for the fine-grained granularity, for example, we use DCT2, DCT8, and DST7. They are the computing of this actor is independent, so we could have parallelism in this unit.
Yeah,
so
okay.
Yeah.
And did you compare the Gantt charts of your execution, the theoretical ones and the real ones?
With the real VVC decoder?
Yeah.
No, not yet. But
okay.
But we aim at implementing this result in real decoder or encoder to see what is the benefit.
Okay, thank you.
I have a question also. When you compare to the theoretical results in several of the curves in the last few slides, what is the theoretical result? Is it just the number of core of your architecture, or is it the Amdahl's law, for example?
The theoretical result?
Yes, the theoretical result that you plot on some of the curves. Where does it come from?
Okay, the theoretical result is it's presenting the optimal case, because while using, for example, a two core, we are supposed to obtain a speed up equal to 2, and the same for on 3. We supposed to have a speed up equal to 3. That's the optimal case.
Okay, I think you could probably refine these figures by using the Amdahl's law. Basically by computing the amount of sequential computations in your, unless everything is perfectly parallel, but I doubt it, you compute the amount of sequential computations in your application, then the amount of parallelizable code in your application, and this will give you a more realistic theoretical result that may be even closer to the experimental results that you have. So your results are very good already on these two curves, but they might be even better than you think if you use the Amdahl's law, for example.
Okay, thank you for the advice.
And maybe I have another question. Did you measure, I think you did, but did you measure the time it was taking to execute the transpose actor in your graphs?
Yeah.
Yes, and was it taking a lot of time, or was it not significant compared to the actual computations of the transforms?
I think that I may have an example.
Yeah, maybe in the scenario you have the figures,
yes.
but I forgot to have a look at it.
Yeah, yeah. It's it's equal to 20. Yes.
Okay.
Mhm.
Okay, so it is still taking quite a lot of time compared to the, I mean, it's useless time because you are just managing data and it takes a lot of time. It was just, yeah, okay, this interests me because it's something that basically it does not serve the purpose of your application, but the overhead is still quite big compared to the time it takes to execute the application. Okay, that's all I wanted to know.
Okay, thank you.
Do we have any other questions? Okay. Otherwise, thank you again for for your
Thank you.
presentation. We cannot clap in a real seminar. We are usually applauding, but here it's
Thank
difficult.
you.
So thank you very much for your presentation.
Thank you.
Thank
Merci.
Thank you.